Okay, recording has started. So good morning, everybody. Welcome back to Math 115. Let's see. Today we're going to kind of continue our discussion. We were about halfway through 5.2 last time. So today I'm going to finish up 5.2 and talk about some of 5.3, and then we will be almost caught up, hopefully. So let me cast the screen. Okay. So where were we? Okay. We were talking about these sum and difference formulas. Okay, so last time we kind of finished up talking about the verification of these identities, which was mainly just about kind of using the identities which we already know to rearrange these things. And sometimes we had to do a little bit of work to make one side a little bit more friendly for rearrangement. Okay, so in this example, for example, we multiplied the denominator by the conjugate, and that was how we made it look nice for us. In the other one, we had to multiply by cosine on the top and bottom in order to make it look a little bit better. Sometimes you have to do a little bit of this rearrangement stuff, but just use your identities that you already know to rearrange those guys until you get something which looks a little bit nicer. Okay, and then we started learning about the sum and difference formulas, and I didn't give you guys a really awesome geometric proof of why these why these formulas are true. If you want to see one, then come and see me during office hours or set up an appointment with me and I can talk with you about it. But these are basically just formulas we use to compute the value of cosine and sine for basically for values of theta which are not angles which are inside of a special right triangle, basically. Okay, or multiples of angles which are in a special right triangle. Okay, so now we can do sums and differences. So for example, we found the sine of 75 degrees, okay, by expressing 75 degrees as a sum of 30 degrees and 45 degrees. And then we had this formula, which is written in white here. I'll circle it in the green highlighter. And that formula, we just say, okay, well, this tells me how to find the sine of a sum of two angles. So if I express the angle that I want to know the sine of as a sum of two different angles, then I just plug one in for x and one in for y, and then I compute the sine of 75 degrees by computing the sine of 30 degrees times cosine of 45 degrees plus cosine of 30 degrees times sine of 45 degrees. Okay, and this is how we use the sum and difference formulas. Okay, so now we know also what sine of 75 degrees is. So we could also find now something like, if we wanted to, we could do find sine of 75. No, we could do sine of 40 degrees. Wouldn't really be an issue. The reason sine of 40 degrees isn't an issue is we can write sine of 40 is equal to sine of, well, we just have to express it as a sum of angles which we already know the value of sine for. And from the previous problem, we now know what sine of 75 is. And I can express 40 as 75 minus 30. So I can find sine of 40 by using the information which I just found out about sine of 75. Okay, so, and so on and so forth. So I can use all of these things to find out, well, what are all of the possible, you know, possible angles which I can express as a sum or difference of angles which I already know. And then once I find out what those angles are in terms of their sine value and cosine and whatnot using the sum and difference formulas, then I can also equip that angle into my kind of library of angles which I already know sine and cosine for, and that will expand the number of angles which I can find a value for sine and cosine with. Okay, so that is about the sums and differences of these guys. So let's warm up now as a class. This is a bunch of office hours stuff. Let's warm up as a class on this problem here. Okay, so our goal is to find cosine of pi over 12 exactly. Okay, and the trick here is that pi over 12 is not an angle which we automatically know, the values of sine and cosine for. So we're going to have to use one of these sum and difference formulas. So let me copy these down. I'll copy down the relevant ones, just the cosine ones, since we're doing a cosine problem. And I want us to try this as a class first for a while. See if you can find out what the answer is to this question. We want to find out ultimately what is cosine of pi over 12. And my hint to you guys is that we can express pi over 12 as a difference of two radian values for which we commonly know the values of cosine and sine, or we can easily find out. Okay, so go ahead and take 2-3 minutes on your own. Give it a shot. And then we'll come back together and you'll be able to see whether your work matches the work of the rest of the class. All right, is there anybody out there who'd like a little bit more time? Please use the Microsoft Teams raise hand button if you want a little bit more time to work on finding the answer to this problem. Okay, doesn't seem like anybody's raising their hand, so we'll start the problem. And before we get to the answer, let's go through the problem as a class and first identify, well, if this is equation 1 and equation 2, which one should I be using for my problem here? Equation 1 or equation 2? Yeah, equation 2, right? Because equation 2 is the one that deals with a difference, okay? And we are given in the hint that we can express pi over 12 as a difference of two angles. Okay, so I'm going to delete this extra identity here because that's not the one we're going to need. We're going to need this identity. Okay. And hopefully most students in the class are able to find that what should go in this question mark here, if we want pi over 12 to be equal to pi over 3 minus blank, well, we can express pi over 3 as 4 pi over 3 minus, 4 pi over 12 minus question mark over 12. And we want it to end up being just 1 pi over 12, so that what should go in here should be 3 pi over 12 or pi over 4. Okay, so if we subtract 1/4 from 1/3, we get 1/12. Okay, so now our goal is to find cosine of pi over 3 minus pi over 4. And that should just be equal to, now I'm going to let this one be x and this one be y. So this is going to be equal to cosine of pi over 3, that's x, times cosine of pi over 4, that's y, plus sine of x is pi over 3, times sine of pi over 4. Okay? Now at this point, what you can do is draw the unit circle twice. On the first unit circle, I will put in the angle pi over 3, which I know is 1/3 of the way to 180 degrees. So 1/3 of the way to 180 degrees is going to be 60 degrees. So it looks like this. So here's pi over 3. And I can also drop a dotted line. And I can solve this special right triangle, since I know that there's a 1 here. Well, I know that this point here is going to have, well, the 60-degree angle is in here, so the 30-degree angle is in here, and then there's a 90 here. So this length is 1/2, so this length is root 3 over 2, and then this is the point, 1/2, comma, root 3 over 2. Okay, and then this 1/2 is going to be exactly the cosine of pi over 3, and then the root 3 over 2 is going to be the sine of pi over 3. Then the next one, we draw another unit circle, and this time we put pi over 4, and hopefully by now we know that the point which we get for pi over 4 is root 2 over 2, root 2 over 2. And these are going to be the values of my other things. Okay, so from here it's just plug and chug. We get 1/2 times, well, root 2 over 2 plus sine of pi over 3 is root 3 over 2. Oops. Times sine of pi over 4 is root 2 over 2. So in the end, it's all over 4. And we have root 2 plus 6. Okay, so if you're not given a hint, can you use either or? That's a great question, Sam. You could use one of the other formulas. For example, you could try to say that pi over 12 is equal to, let's see, negative pi over 4. Well, this is kind of the same, I guess. Negative pi over 4 plus pi over 3. I guess that's really more of a rearrangement. And then you could use the sum formula. So that would work. Or you could say that pi over 12 is equal to 7 pi is coterminal. To 7 pi over 4 plus pi over 3 or something like that would also work. Okay, but the key here is to express pi over 12 as a sum or difference of other angles which we already know. So if you can find a way to express pi over 12 as a sum of angles we already know, then that's fine. Or if you can express it as a difference of angles that we already know, that's also fine. And you can use either thing and you'll wind up with the same answer. Yeah, okay, Abdul Rahman's got a tip for everybody. If you convert this to degrees first, you might find that it's a little bit easier to work with if you have a better kind of intuitive grasp of what a degree is. Then this is like 15 degrees, and you can express 15 degrees as 60 degrees minus 45 degrees. So that's one way that you could think of this problem as well. If you want to use degrees, that's always fine. You can do whatever you want in this world. Okay, let me survey you guys. How do we feel about this problem? Relatively good or comparatively poorly? Poor. Poor? Yes, poor. Okay, sure. I didn't even say 1 to 10, but let's get the 1 to 10s out. We got 2 9s so far. Some goods. Is there anything particularly confusing about this problem for you guys? Okay, seems like not. I think the most confusing part is figuring out probably which identity to use. We know we should use one of the cosine identities because our function is a cosine function. And if we didn't have this hint here, I think that this would be kind of the hard part here, would be figuring out how to express pi over 12 as a sum or difference of angles, which we already know. That's, I think, the trickier part. Okay, and I think it's also, this problem is maybe a little bit easier in terms of the context. Like we are right now, we're studying the chapter on sum and difference identities. So it's already kind of top of mind that we might want to use those. But if you saw something like find cosine of pi over 12 on the exam, you might not immediately recognize that we should use the sum and difference identities to begin with. So recognize, I think the key information here is that if we want to find the sine or cosine of an angle which is not a 30, 60, 90, or 45 degree angle, we basically have to use either one of these formulas, these sum and difference formulas, or one of the so-called double angle formulas or half angle formulas that we're going to learn later on. Okay, so context is making this maybe a little bit easier than it might be otherwise. So recognize when we have an angle which we don't like, we need to somehow express it as a sum or difference of angles that we do like. That's what I think is the most confusing part. Without a hint, then, how do you know which angles to use? Yeah, that's a great point. I mean, you just have to basically know that in your word bank, you know how to do 30, you know how to do 60, you know how to do 45, you know how to do 135, you know how to do 90, you know how to do 120, you know how to do like 150, you know how to do 180, and so on and so forth. Okay, so you have like this word bank of angles which you know how to do, okay? And then you have some angle like, I don't know, 105. And you have to check, well, are there any numbers in here which I can subtract from one another or add to one another that is going to get me 105? The answer is, well, yeah, we can take 65 or 60 plus 45. Or if we had to find the angle, if we wanted to express this as a difference, we could do like 135 minus 30 would also be fine. You know, stuff like this. So it takes a little while. You just have to check what is this number and how can I build it from the ones that I know. Okay, I think I've said enough about the sum and difference identities. What I want to talk about now are what we call the cofunction identities. Okay, and this is the first time I've ever heard the word cofunction. Well, maybe it's not. Maybe I heard it at some point, but it's not super well known by this name, I guess, but this is one name that you can use to talk about it. Okay, and what does it say? It says that cosine of pi over 2 minus x is going to be equal to sine of x. Okay, cosine of pi over 2 minus x is going to be equal to sine of x. So let's really kind of parse what that means, because this first one looks like a transformation of the cosine function. And then the second one is just the sine function. So why don't I graph the sine function first, and then we'll try to graph what does the transformed cosine function look like. Well, the sine function just looks like this, and so on and so forth. So here's sine of x. And now let's draw a cosine of x and transform it in the way that we see here. So cosine of x would be if we start at 1 and then come down to 0, and then we're down at -1, and then we cross, and then when this thing reaches a max, we're at 0 again. Oh, crap. Like this. And so on and so forth. Okay. So this is my really bad cosine function. Well, what does cosine of pi over 2 minus x look like? Well, cosine of pi over 2 minus x is the same as doing cosine of negative x plus pi over 2. And if we remember, what we should do is we should apply horizontal shift first. So what we're going to do is we're going to take our cosine function and we're going to move it pi over 2 units to the left. Okay, and then we're going to reflect. Okay, so if I move cosine pi over 2 units to the left, it's going to look more like this. And then if I reflect about the y-axis, so this is cosine of x plus pi over 2. We moved everything to the left by pi over 2 units. And now if I reflect, then I'm going to have a graph which, each point on this side is going to come over exactly onto the sine graph. Okay, and this point likewise is going to come over directly onto the sine graph. And then this point here, this point here is going to go directly over onto the sine graph, right? So if we reflect, we're going to wind up getting something which is basically right on top of sine. So this is cosine of pi over 2 minus x. Hopefully these colors make it clear enough. This is supposed to just show you what is the kind of order of the transformations here. And we can see that if we apply these transformations to the cosine function, we get a function which is basically overlapping with sine of x. Okay. And if we do the same thing for number 2, then we get if we transform sine in the same way, then we get cosine. Okay. So the same exact transformation applied to either of these functions gives us the other one. Okay. And what is this really encapsulating? This is really just encapsulating the fact that sine and cosine look like the same function that's just been moved over a little bit. Okay, so if we take the whole thing and up and move it a little bit, it'll look up the same, basically. Okay, so this is about the cofunction identities. They just say that, well, they say a little bit more than just that sine and cosine are a phase shift of one another. They also say something about the symmetry of the functions. They say one is a phase shift of the other, and also if we reflect it, then that phase shift is also kind of still accurate. Okay, so the cofunction identities really say just a little bit more than saying that these two functions are each other just up to a phase shift, which is also true. Okay, so let's verify now a couple other identities. And these are more of like the stereotypical phase shift identities, I guess, is what you might call it. Why do I call it a phase shift identity? Well, I call it a phase shift identity because the transformation that's happening on sine of x plus pi over 2 is exactly a phase shift. So phase shift identity. Okay, well, if we want to verify this, we can do it easily from the graph. Just say, okay, take a sine function, which reaches the maximum at pi over 2, and then take the whole thing and move it over pi over 2 units. Well, what does it look like now? Except for cosine, right? So that's one way to view this. The other way to view this is, well, if you imagine the unit circle, then we have these 4 points, 1, 0, 0, 1, 1, 0, sorry, negative 1, 0, and then 0, negative 1, right? And the sign tells us about the y values, right? And the y values go 0, 1, 0, negative 1, 0, 1, 0, negative 1, and so on and so forth, on and on forever. Whereas the x values go 1, 0, negative 1, 0. So what this is saying is if we start counting the sine at pi over 2, and if we start counting the cosine at 0, then as we go around, we're going to be hitting the same numbers, okay? So if the sine count is pi over 2 in front, then basically, what is this really saying? It's saying that, let me see if I can make these colors match up for you guys. It's saying, well, essentially, this 1 is equal to this 1, and also this 0 here is equal to this 0 here. The y value of the coordinate on the left side has the same value as the x coordinate of the point on the top. And then the y value here at negative 1 down below has the same y value as the point on the left side has x value. And then again, finding out our colors, this y value here of 0 has the same y value as this point down here has x value, right? And if we just go around in a circle, the sine pattern is, 0, 1, negative 1, 0, 0, 1, 0, negative 1, and so on and so forth. And then the cosine pattern looks really similar, right? So that's another way to see that. Okay, and likewise, if I instead moved the whole thing over pi over 2 units to the right, okay, so let me reset my graph here. My original sine function looks like this. If I move everything over pi over 2 units to the right this time, well, then I'm going to get something which looks a little bit different. This doesn't quite look like a cosine function, but it looks like a cosine function if I were to reflect it about the y-axis. So if I were to reflect this cosine function about the y-axis, sorry, about the x-axis, excuse me. Okay, if I were to reflect cosine, then the graph of this thing would be the graph of negative cosine of x. Okay, so if we phase shift sine to the right by pi over 2 units, we get something which looks like a reflected cosine graph. Okay. There's one other way to verify these identities, which will be the last way that I show you guys because I feel like I'm really beating a dead horse at this point. The last way to do it is to say, well, we have these sum and difference identities, so let's use them. Let's use the sine one. Sine of a sum of angles. Okay, so this is the thing we're trying to find out. And now let's try and use sine of x and pi over 2. So if we want to do this, and our angles are, well, we have sine of x plus pi over 2, well, we're going to put a pi over 2 anywhere we see a y. So we get sine x times cosine of pi over 2 plus cosine of x times sine of pi over 2. And if we look at the unit circle and what's going on at pi over 2 is facing straight up. And the point up here is the point 0, 1. It has y value 1, so sine of pi over 2 is 1. And it has x value 0, so cosine of pi over 2 is 0. So this whole term goes away because we multiply by something which is equal to 0. And this whole term just becomes cosine x, because we multiply cosine x by 1. So in the end, we get cosine of x. So that's how we can do it using the sum and difference angles, or sum and difference formulas. So this is more algebraic kind of method. Okay. Any questions about the phase shift identities or about the cofunction identities? I'm hoping that these are sort of intuitively clear to you guys based on the graphs of the functions. Have I made that clear enough for you guys? What do you think? I think so. Might be easier if I showed this with Desmos. Let me give you a quick recap of what's going on here using Desmos. So, okay, let's say we have functions, sine of x. Okay. Here's the sine of x function. And we can also graph cosine of x. Here's cosine of x in blue and sine of x in red. So we can see that these functions look the same, except one's kind of moved over a little bit. So we can imagine that if we shifted, okay, if we shifted sine of x to the right a little bit, we moved the blue curve to the right a little bit, then it would be right on top of our red curve. Okay, so if we did sine of x plus, oh, I don't even know how to do pi on this thing. Oh, there it is. Pi over 2. Then look, well, that's not even that great. Pi over 2.1. Okay, so you can kind of see now. If we did 2.1, then they'd be almost on top of each other. And it's kind of hard to see, but if we make this 2.1 exactly 2, then they're on top of one another. Okay, so we move it over, and then they're on top of one another. Okay. I think it's clear. Great. All right. Then we're going to move on and talk about double and half angle formulas. Okay, so the double and half angle formulas are, for calculus, without a doubt, the most useful ones to know. So if you were going to move on from this class to calculus, then this would be, and you were only going to pay attention to one section of all of the trig stuff, this would be the section that I would pay attention to. Actually, I'd pay attention to all of the sections, but this one especially. Okay, so the double and half angle formulas are really useful in calculus, and I'll explain why a little bit later. Okay, so let's look at what the double angle formulas are, and I'll explain why they're called the double angle formulas. They're called the double angle formulas because in the expression on the left, the angle which is inside has the value 2 times the value of the angle which is ultimately on the right-hand side of our formula. Okay, so we have sine of 2x is equal to sine of x times cosine of x times 2. Okay, this is one formula we have. Another double angle formula we have is that we can turn cosine of 2x into cosine squared x minus sine squared x. Okay, and we could also kind of rearrange this if we added cosine x and subtracted cosine x in the middle. So if you want to go from here to here, you would say this is cosine squared x, and then you'd do it like a plus minus thing. Plus sine squared x minus sine squared x minus sine squared x. And then this first part here is 1, because cosine squared x plus sine squared x is 1. That's a Pythagorean identity. And then the second part here is minus 2 sine squared x. Okay, so these are the double angle formulas. And they tell us how to take something whose angle has this annoying 2 attached to it and write it as something which is not so annoying. Or more often, we go from the right-hand side to the left-hand side, at least in calculus. Okay, the reason is when we want to do calculus on these functions, working with a function like sine of 2x is much, much easier than working with a function like 2 sine x cosine x. Okay, because 2 sine x cosine x involves a product of trigonometric functions, and that makes calculus very painful. It's much, much easier to then just have one single trigonometric function, and if we have to have this 2 hanging out inside, that's not really a big deal. Okay? Or especially if we have something like 1 minus sine squared x, 1 minus 2 sine squared x, it's definitely way, way easier to work with something like cosine x than it is to work with like a square trigonometric function. Okay, so products of trig functions are really not very friendly to calculus. So we like being able to use these formulas to take those pesky products of trigonometric functions and express them as a single trig function. Okay, so this is the really useful property about these identities. Okay, these ones are called double angle formulas. Okay, so let's see here. So here's a problem which we could use the double angle formulas to solve. This is a 2 theta, and this is a 2 theta. So what are we given? We're given the following. We have cosine of theta is 3/5. Okay, cosine of theta is 3/5. And theta is in quadrant 2. Okay, and we're supposed to find out what is sine of 2 theta and what is cosine of 2 theta. So let's first, before we do anything, let's draw what theta looks like. Well, you have a unit circle. Theta is in quadrant 2, okay? And I know that the cosine of theta is 3/5. So I know that the x value of the point on the unit circle should be 3/5. 3/5 is like 60% of the way to 1. Oops. So I'm going to draw that like right here, maybe. And theta points right there at that point. And we can drop a line and draw our triangle. and then this will be a right angle, and this is the point -3/5, comma, oh wait, cosine of theta is 3/5, and theta is in quadrant 2. That makes no sense. Hang on a second, I gotta check the book here. I must have written this down wrong. There's no way I wrote okay, yeah. Cosine of theta is equal to -3/5. Okay, sorry about that. So please make that correction in your notes. This should be a -3/5 in the problem. Okay, so this is the point -3/5, comma, y. I don't know what y is. I could use the Pythagorean theorem to figure it out. But let's see what do we think is going to happen with these functions here. Okay, so we know that sine of 2 theta, using our double angle formula, is going to be equal to 2 times sine of theta times cosine of theta. So we are asked, actually, if this is theta, if we were to take that angle and double it, okay, it looks like, I don't know, 135 times 2 would be like 260, so it'd be like somewhere, if we were to double it, it'd be maybe somewhere down here. And we are asked, ultimately, what is the y value of this point? Okay, and the point is that we can find the y value of this point purely by knowing things about the x and y values of this point here. Okay, because that is the relationship here. This would be cosine 2 theta, and this would be sine 2 theta. Okay, so we can find out what those two values are by looking at the values of cosine theta and sine theta. Okay, this is the beauty of the double angle formulas. Okay, so if cosine theta is equal to -3/5 and theta is in quadrant 2, we're supposed to find sine of 2 theta and cosine of 2 theta. So far we know what cosine of theta is, but if we want to find out what sine of 2 theta is, we need to know both what sine of theta is and cosine of theta is. We know cosine of theta is -3/5, but we need to know what is sine of theta. So in particular, we need to know what is the y value of this point on the unit circle. So I'm going to take this triangle out and solve it using the Pythagorean theorem. If I have a triangle which looks like this, and I know that this side length is 3/5, and I know that this side length is 1 because it's the side of it's a radius on the unit circle, I can figure out what this side length is using the formula a squared is going to be equal to 1 squared minus 3/5 squared. So I get a squared is equal to 25 over 25 minus 9 over 25 is 16 over 25. And then if I square root both sides, I'll get a should be equal to 4/5. So I know that the y value of this point here is actually 4/5. That feels really wrong. I guess not. It's a 3, 4, 5 triangle. Okay. -3/5 has a height 4/5? That seems like impossible. All right, sorry, people. I think I'm just wigging myself out today for some reason. All right, so, I mean, the Pythagorean theorem doesn't lie. So this is going to be 4/5. So if we want to know what is sine of 2 theta, well, we just take 2 times 4/5, that's sine of theta, times negative 3/5, which is cosine of theta, and we get 2 times 4 times negative 3 is negative 24 over 25. And what is that telling us? That's telling us what is sine of 2 theta. So the y value of the point in red is negative 24 over 25. So hey, it looks like our drawing was pretty close, actually. This red line is going to be really, really close to that 270 mark, because this number is really close to negative 1. Okay, and then what about cosine? Well, cosine of 2 theta, we have two options. Option 1 is to take 1 minus 2 sine squared of x, and option 2 is to take cosine squared x minus sine squared x. Well, one of them involves fewer operations. I'm going to choose the I'm going to choose the one on the bottom, because then I only have to do sine squared x and multiply by 2. That's no problem. Whereas the above one, I have to square two things, so I guess that's a little bit more work, but either will be fine. So I'm going to use number 3. I know that cosine of 2 theta is going to be equal to 1 minus 2 sine squared of theta. Sine squared of theta. Well, I know that's 1 minus 2 times, well, sine of theta is the y value of the pink point, which I already established is 4/5. So I take it and I square it. And what do I get? Well, 1 minus 2 times 16 over 25 is equal to 1 minus 32 over 25 is equal to 25 minus 32 is negative 7 over 25. So in this case, the x-coordinate of this point is negative 7 over 25. Okay, so, man, I feel like this is just like a really not very exciting problem to work on. Just, applying the double angle formulas. Okay, but this is really not any different from any of the other problems that we've been doing so far. Is we're given some information about basically the right-hand side of these identities, and we're supposed to then spit out, well, then what should the left-hand side look like? Okay, so in our identities, we know basically what is sine of x, and we know what is cosine of x. And so we're then supposed to be able to infer what is sine of 2 times x using the formula. Okay, or for the other ones that we did, we did that one, and we also had this one here at the bottom. We said, well, we know what sine of x is, so I can square it and then multiply by 2, no problem, and then subtract that from 1, and that just gives me what the cosine of 2x should be. Okay, so it's kind of like the same game as the sum and difference identities. I just want to find a way to express the thing which I want to know about as some kind of expression involving things which I already know. Okay? So one should be careful in these problems you know, when we're doing these double angle formulas, when we're doing the sum and difference formulas, you know, it's really kind of an extra layer on top of already needing to know how to find the cosine and sine of a given angle. Okay, we need to know how to find the cosine and sine of a given angle, and then how to apply these formulas to then use those numbers to come up with something new, which is ultimately, you know, the x and y value of this red point on the unit circle is what we were after. And we found it by using the information which we knew about. This was 2 theta, basically. We used the information which we knew about the angle theta. We knew about the point on the unit circle which was associated to theta, and we used these double angle formulas to find out what x and y should be without actually having to, you know, really have any information whatsoever about this point before the fact. Okay, so this is the sort of power of the double angle formulas, is it shows you, it tells you something more about another point on the unit circle which you really know nothing about, based on some other point which you do know some things about. I think that's as concisely as I can put it. Any questions about these double angle formulas? Or about the problem, the example problem? Okay, seems like no questions about these. Okay, so let's talk about the power reducing formulas. Okay, so these are the so-called half angle formulas, and they are by far and away the most useful trigonometric formulas probably in the history of trigonometric formulas. Okay, and the reason that they are so useful is they turn these two functions, which we hate, okay, we don't like these ones, they turn them into these expressions, which are very friendly. Okay, this is the good thing about the half angle formulas. Okay, they turn these awful cosine squared x and sine squared x functions into 1 plus cosine of 2x over 2, or 1 minus cosine of 2x over 2. Okay, let me show you why that's great using Desmos. Let's just look at what even does sine squared of x look like? Well, if I take sine of x and I square it, it's not so easy to see. Here, let me see if I can put sine x in here as well. Or maybe cosine x. Okay, so this is my original, this is a cosine function here in green. And sine squared of x looks like this thing, okay, which is all kinds of wiggly and a little bit irregular. And all of the nice properties that we have derived about sine fly straight out the window when we start squaring it, okay? First of all, it's, you know, it's not going to have as nice of a period. Okay, it's going to be a lot more wiggly. And also, you can see that it's always positive, right? If we take any number and we square it, we get a positive number or 0. Okay, and this is just going to basically have zeros anywhere that the sine function had zeros, right? Because we take 0 and we square it. But instead, basically, where it would have crossed beneath the x-axis, we actually have this bouncing behavior, which is just really, really annoying. And in particular, for doing calculus, okay, when we want to, say, take a derivative, or more importantly, when we want to take an integral of the left-hand side, taking an integral of something like cosine squared x is literally impossible. Well, okay, I don't know about literally, but it's pretty much impossible. And taking an integral of the right-hand side is a piece of cake. So this is why we care a lot about these formulas, okay? So if you remember one thing, let it be that cosine squared x and sine squared x are the devil, and we would much rather work with these fractions on the right-hand side. Okay, so why do we call them power reducing? We call them power reducing because the original power here was 2, and in the expression on the right-hand side, we only have a power of 1. Okay, so hopefully you guys are convinced that these are awesome. Now let's try using one. Okay, let's try finding sine of pi over 12 using a half angle formula. So first of all, you might think if you were asked on an exam to use sine of pi over 12, well, you could try to write this as sine of pi over 3 minus pi over 4, and then use a difference formula. Perfectly acceptable way of approaching this problem. I'm going to show you how to do it using a half angle formula, just so that you see how these guys work. Oh, hang on a second. This should have been a sine squared. It should have been a sine squared of x. Sorry. Dang, how did I write so much stuff wrong on these notes? So this was sine squared of pi over 12. So what you could have done is found sine of pi over 3 minus pi over 4 using a difference formula and taken whatever you got from that and then squared it. And that would be a fine way to approach this problem. But you can also use one of our half angle formulas here. Okay. So here's what's going to happen. We're going to use this second one here. So rather than computing sine squared of pi over 12, I'm going to compute 1 minus cosine of 2 times pi over 12. And I'll take all of that and divide by 2. Well, 1 minus, this becomes 1 minus cosine of pi over 6, which, remember, this is 30 degrees, over 2. And then cosine of 30 degrees is root 3 over 2. If you want to see why, here's a quick show. You'd put 30 degrees here, and then this would be a 30, 60, 90. And then this side here would be 1/2, and this side here would be root 3 over 2, and this side here would be 1. So the cosine is the x value, so it's the root 3 over 2. So 1 minus root 3 over 2 over 2. So that's our answer. Maybe you could clean it up a little bit. You could write 1/2 minus root 3 over 4. Okay, so that's one way we can compute this using a half angle formula. Okay. Or I guess you could write 2 minus root 3 all over 4. That would also be okay. Okay, so, again, trig is really one of those areas of math which is, in a way, I mean, really beautifully connected, in the sense that if you want to approach a problem, you have a lot of options. I think that's beautiful because that tells you something about how well connected everything is in trigonometry. You can use the unit circle, you can use the triangles, you can use the trig, you can use periodicity, you can use the double angle formulas, you can use all sorts of geometric interpretations and all sorts of things involving the graphs of trigonometric functions, and it's all very, very complete and well connected. So I think that's great. Some students might find that a little bit overwhelming because it's like, well, which one should I use? And the answer that I would give to that student would be, use whichever method makes you happy. I'm not one of those instructors that's going to, say on an exam that you have to do something using a certain method, and if you use any other way, then it's wrong. No, I like students who think creatively and use it. If you use a method that I didn't think of, I think that's great. That just shows that you're mathematically creative. So hopefully you find some way to approach each problem, and which way is less important than having a way. Okay. Another example would probably help a lot. Sam, were you referring to the double angle formulas? Okay, maybe I'll do one more example of the double angle formulas. And then we'll be done for today. Okay, so let me see if I can think up another example.
Thank you. I'm Dee. I'm the Salesforce admin. I work mainly in Salesforce, but help with reporting in like trial, as well.
Where did I put that?
Something that I like to do outside of work is hiking. Me and my husband are both really big hikers. So I've been to Tahoe and all the national parks around there.
Okay, so let's see here. How can I come up with another problem for the double angles? Maybe I'll use a problem from the book.
Former premises. Yes.
Okay, we'll do this one. Supposed to find 1 minus sine squared of 15 degrees.
Cabinet. Here it is.
Okay, so here's a problem where we're given something which really doesn't look very friendly at all. Okay, doesn't look very friendly at all. So one way we could try to approach this is to focus in on the sine squared of 15 degrees and then look at a half angle formula and say, well, if I plugged 15 in here for x, then over on the right-hand side, it would become cosine of 30, and I'd know how to find out that angle fairly easily. So that'd be one approach. Okay, but the other approach would be to recognize, well, this looks really familiar. It looks like the right-hand side of one of our double angle formulas. Okay, so if we go back to one of those, let's see here, which one I'm talking about. I'm talking about this one here. Oh, come on. I forgot the 2. Of course I forgot the 2. Okay. So looking at number 3, we can copy that one down. We know this is going to be equal to
South Carolina just
cosine of 2 times 15 degrees. using our double angle
So
formula.
I might be able to get mine soon.
So if I want to know what the answer is to the left-hand side, which is kind of very unfriendly, I can instead rewrite using the double angle formula.
Yeah, hopefully. I looked yesterday, but there's no open appointment.
And
so
we get
my husband
cosine of 30.
His second shot this Saturday, so I think I might just drop in and be like, hey, pharmacist,
Okay, so
can I get my shot?
sorry, my wife is having a meeting in the background. So cosine of 30 degrees is a lot more friendly. We just look at the unit circle and, as usual, we draw a 30-degree angle in here, and then this triangle is a 30, 60, 90 triangle. So this side has length 1/2, it's across from the 30. This side has 1, it's across from the hypotenuse, or from the 90. And then this length here will be square root 3 over 2. So we get that this is equal to the square root 3 over 2. So that's one other way that we can use these double angle formulas. Okay, so when we see questions asking us to find the value of some really unfriendly looking expression like this, the first thing that I would check is, well, find all of the double angle, half angle, sum product identities, and just check if what we have matches any of those directly. And if so, then great, and we can just kind of take this approach. Okay, or if not, or if we don't immediately see one that, matches, then we can be a little bit more resourceful and say, well, maybe 1 minus 2 sine of 15 degrees, sine squared of 15 degrees would be equal to like 1 minus 2 times sine of 15 degrees squared. And I know how to find sine of 15 degrees because this is 1 minus 2 times sine of 45 degrees minus 30 degrees, quantity squared. And then this inside thing can be found using a difference identity. Okay, so what is the point of all this? The point is that if you get stuck on these problems, you have a lot of options. Okay, and really, if you wanted to just never learn the half angle formulas, you could get away with it as long as you knew the double angle formulas really well. Because if you know the double angle formulas really well, you can do everything that you can do with the half angle formulas. And if you know this, and the double angle formulas and the half angle formulas both come ultimately from the sum and difference formulas. So, you got options on these problems. Okay, any other questions about the double and half angle formulas? Okay, if not, then I think we'll close for today here. We made it through everything. We got caught up. Next time we'll talk about product to sum and sum to product formulas. So it's going to be still dry for a little bit while longer before we get into some more interesting stuff. But I hope you guys have a good weekend. I'm going to post a practice exam hopefully tomorrow, and then a solution video will go up soon. So give those practice exams a try. Hopefully, please bring your questions to class next week and to office hours next week and to the SI sessions next week. Your exam will be a week from today. Good luck studying, and yeah, have a good weekend, everybody.